That brings us to the binomial distribution. So binomial distribution, it's what we were talking about basically in binomial probability, where we're going to keep repeating a Bernoulli trial. We're just going to do multiple Bernoulli trials. So x will represent our random variable denoting the number of successes in the Bernoulli trial. There it is. It's exactly what we saw with binomial probability, written slightly different, but there it is. NCX, probability of happening to the power of x, probability of not happening to the power of n minus x. P, probability of success, x is the number of successes, n the number of trials. As I say, exactly what we just saw in binomial probability. Well, let's now draw up a distribution table. Let's go and find our expected value and variance for a binomial distribution. So here is the table, a little bit harder because of course we don't know how many trials there are, and our random variable is representing the number of times it happens. So it could be 1, it could be 2, it could be all the way up to n, whatever the number of trials is, but I know those individual probabilities now thanks to binomial probability, so I can create what we need. So this expected value would be the sum of the xpx column. So there it is, the sum from 0 to n of k, nck, p, k, q to the n minus k. I can play with this a little bit. So what I've done, you'll notice, is I have pulled out the first term, which is when k equals 0. Why? Because that's just equal to 0, because it's going to be 0 times that disappears. I'm left with 1 to n of this expression. But I could rewrite that a different way. This will give me exactly the same terms as the one above. So it's just slightly different, but it will give me the same. Now, why do it that way? Well, because here I can now pull out this common factor of n. So I now have np times this. But what is this? That would be the same as k equals 0 to n minus 1. Again, I'm just playing with the numbers. Instead of starting at 1, I'm starting at 0, which means instead of finishing at n, I finish at n minus 1, but that also means I'm no longer substituting into k minus 1, I'm substituting into k to get the same numbers. But that is the sum of the probabilities p plus q. P plus q we know is equal to 1, therefore we get our formula np. Now do not panic, they're not going to ask you to derive this, I'm just showing you we can prove that yes, it is np. So there's expected value. Variance, a little bit more tricky to work this one out. So expected value of x squared minus the average squared. I'm going to rewrite x squared in an interesting way. I'm going to rewrite it as x times x minus 1 plus x. Alright, why do that? Remember, you may recall our rules for playing with expected value. I can split up the expected values. So now I'm saying expected value of x times x minus 1 plus the expected value of x, which we just worked out, was np. The average squared then is n squared p squared. So now I just need to work out the expected value of x times x minus 1. Okay, well that would be this particular sum. I've got to play around with this now. Well, if I pull out k equals 0 and k equals 1, pull out those terms, and now this expression goes from 2 to n. But 2 to n, well these first two are just equal to 0, so they go away. 2 to n, pull out the n minus 1, but now I've got a sum which is like I did before. Well hang on, that's just a row in the distribution table, p plus q is 1. I get n minus 1 p squared, but remember that was just expected value of x, x minus 1, so to work out variance I substitute that back in, and look what happens. Isn't it beautiful? We just end up with npq. Again, don't panic, you're not going to be asked to derive that, but npq. This is what you can quote. If x is binomially distributed, the two pieces of information we're interested in is the number of times we're repeating the trial and the probability of success. So n and p, they're the two bits of information we're interested in. The expected value will always be np, the variance will be np 1 minus p, often we just call that q, but 1 minus p. Here's the interesting thing, if you were to look at the graph of the distribution, if p is less than a half, so if the probability of success is less than half, your distribution should be positively skewed. If it's equal to half, you should have a nice symmetric distribution. And if the probability is greater than half, you should have a negative skewed distribution. That's what you should be seeing on that graph. Alright, so we're going to state whether a binomial distribution could be used for these problems. And if it can be used, we'll work out the parameters and so on. Got a dice, standard dice, going to roll it 10 times, find the probability of getting 3 4s, 3 5s, and 3 6s. Could I use a binomial distribution for this? And the answer is no, because you've got 3 different things you're interested in. Remember, you have to be able to define your random variable to what you're interested in. Now, 3 4s, 4 5s, and 3 6s, they're 3 things that could be changing, not just one thing that could be changing, so no good. That's not binomial. If you wanted just the probability of 3 4s, fair enough, because now it's just one thing you're looking at. Or similarly, 4 5s or 3 6s. So it's just one outcome you're looking at. Going to toss a coin until a head occurs. Probability that 8 tosses are necessary for this. Again, no. Because here, the number of tosses is unknown. Now, binomial distribution requires a fixed number of events. What are the 2 key pieces of information we need? How many times are we doing it, and the probability of success? We don't know. So how can we work out 8 tosses are necessary when we don't know how many tosses we're doing all up? Not binomial. Okay. We have a jar, the balls numbered 1 to 49, we're going to select 6 balls at random. Probability that 4 of the 6 have an even number. Now it just depends on whether you're putting the ball back in or you're not. Remember, your Bernoulli Trial, probability has to be the same every single time. So if it's without replacement, no good, because the probability is going to change each time. If it is with replacement, it's good, we can do it. X would represent the number of balls with an even score. This is something we can measure. So X is the number of balls with an even score. It would be binomially distributed. We're doing it 6 times. We're pulling 6 balls out. Probability of success, there are 24 even balls in our jar. So probability then, we could work it out. We want exactly 4. So we're basically playing with the binomial probability there. And we get 0.2247 for that one. 3 trials of a binomial experiment. Probability of X is as follows: 0, 1, 2, 3. Probability of success at 1 trial. We have a binomial distribution. 3. We don't know the probability of a single outcome here. That's what we're working out. So I'll just leave it as P. But what I do know, I could pick any one of them. It makes sense to choose the easiest one, so I've just gone with 3. So P, probability that X equals 3, we know is 0.027. The binomial probability for that would be 3C3, P to the power of 3. 1 minus P would therefore be to the power of 0, which is 1. That's why I chose the third one, to make it a nice, easy equation to solve. So P cubed is 0.027, so it must have been 0.3 probability of success for that one. So what would the variance of this distribution be? Ah, well, NP cubed, or NP1 minus P, multiply the numbers together, 0.63. All right, let's have a look at these distributions. Which is which? I think the first one's probably easy enough to look at and go, oh yeah, that's the symmetric one. But which one is the positive skew and which one is the negative skew? And I always think these are named the wrong way round, because actually the one where they're all pushed to the positive numbers is the negatively skewed number. There's a negative skewed graph, and the one where they're all pushed to the negative numbers is the positively skewed graph. I always think that's named the wrong way around. But anyway, negative skew is when they're pushed to the positives. Positive skewed is when they're pushed to the negatives. So of these 3 distributions, which one would have an individual trial with a probability greater than pi on 5? Well, pi, approximately 3.14158976932288419793993755105820751058207816406228 approximately. But it is bigger than 2.5. So we know the probability here is greater than a half. Therefore, it's the negatively skewed, because if it's greater than a half, it's going to be pushed to the right-hand side. Because half, less than a half's on the left-hand side, greater than a half on the right-hand side. So it's negatively skewed. X is a random variable. Here it is defined. 150 trials we're doing. Probability of success is 2/5. Standard sort of question. Find the average and the standard deviation. So it's just a matter of simply going, oh, well, the average is NP, 60. Deviation is where you've got to be careful. Remember, it's variance that is NPQ. So 36. Therefore, the deviation is the square root of that, 6. But what if we wanted to raise that average to 100? How many more trials would we need? Well, 100 would now have to be n times p. It's n's what we're trying to find here. Simple little equation. N has to be 250, but make sure you answer the question. The answer is not 250, it's how many more are needed. So we need another 100 trials to get the average to 100. What effect does this have on the standard deviation and the distribution? What effect would it have? Well, if I work out the new standard deviation, it's now 7.75, which is a bigger number than 6. And standard deviation is a measure of spread, how far away from the centre of the data. So therefore, it's more spread out. We have a larger spread. So it's going to move away from the average. We have an experiment. 2 dice are rolled 10 times. The number of times the sum equals 7, which of course is the most common outcome when you're rolling 2 dice, is noted. Find the mean and the standard deviation of our distribution. I'm interested in looking at the number of times the sum is 7. So that's going to be my random variable. X is the number of times the sum is 7. Well, I know it's binomially distributed. We're doing it 10 times. Probability of success, well, the probability of the sum being 7 is 1 in 6. Average NP, we get 1.67, and variance, NPQ, but we want standard deviation, so we'll find the square root of that, 1.18. Now we've gone and simulated this experiment 1,000 times. Reality is I didn't go and roll 2 dice, I got a computer to do it, but these are the actual outcomes from a simulation that I did. Notice the change in the pronumerals, because this is now a sample rather than getting the whole population. So technically we now talk about relative frequency rather than probability and things like that. But there are the answers, the results of the experiment. Find the mean and the standard deviation of the simulation. So for average now, because it's a experimental one, I use X bar rather than mu. Mu is what you use when you're talking about the population results. X bar is what you use when you're talking about a sample. It's probably not that big a deal, to be honest. Often people use the wrong ones, but technically that's what it is. So instead of saying X times P, I'm saying X times the relative frequency. Again, it's the same thing. 1.633. And variance is S rather than sigma when we're talking about a sample. So we end up with 1.500311. So there's my deviation, 1.22. It would be nice if it was exactly the same as the theoretical probability, but remember what should happen, the more times you do a trial, the closer and closer the results will get to the theoretical probability. In fact, if we were to draw both of them, that's what these ended up with. So the orangey one there is the theoretical probabilities, the blue ones is that particular simulation that I did. And it's not too bad, actually, when you look at it. It's quite good. I might have just got lucky, because remember, it was just totally random what happened. Anything could have happened. All right, that shall do us.